Hello, and welcome to a talk on an introduction to how one searches for pulsars. I'm really sorry that it's not possible again for us to be there with you today. Really am missing that opportunity to interact with you directly, but they will be available at the end of the presentation for you to ask any questions. So you will have already in previous sessions had an introduction to pulsars in general, but today what I wanted to talk to you about was how do we actually find pulsars? And then at the end, I'll touch on some of the uses that we'll put those pulsars to. But right at the start, just to refresh your memory, I'm going to talk about what pulsars are, because it's been a little while since you previously heard me talk about this. Then I'm going to talk about the three different ways that you can find pulsars. One is via single pulses, so just a single detection of a bright burst of radio emission. And then two other methods which rely on the regular periodicity of pulsars to enable us to be able to detect them. And these are called the fast Fourier transform and the fast folding algorithm. Then I'm going to discuss how do you decide where you want to look. So where do you point your telescope to increase your chances to find pulsars? Or perhaps you want to understand the galactic population of pulsars in its totality. And then we'll talk about why we want to go and find new pulsars. What are the reasons that we think it would be useful to find new pulsars? And in particular, we'll be talking about what types of pulsars there are, how we can use these pulsars for some gravity studies, and then lastly, I'll touch on the equation of state of what's called supranuclear density. So that is the material inside the neutron stars, which we showed last time we had a presentation on pulsars, is incredibly dense. So just a reminder, what are pulsars? Well, at the end of the life of a massive star, so somewhere between 9 and 15 or 8 and 20 solar masses, we expect the stars to evolve up the main sequence as shown here on the right-hand side, and then evolve very rapidly through off the main sequence. And then they will eventually run out of fuel. So they will have burnt all of the material inside them, until right in the center in the core, there's only iron. And then what happens is that there is no nuclear fusion going on anymore. And so these stars will can't support the weight of the material above them. And the star will actually collapse. And then that collapse hits a solid surface, which is the dense core. And then there is this so-called supernova explosion. And we can see that here in this animation, where you can see a star. Now you can see it goes supernova. You can see the material that is blown off out into space, which leaves behind the so-called supernova remnant. And in the center, we have a neutron star. So a star predominantly made up of neutrons. It's collapsed from its original massive size down to something which has a radius of just 10 kilometers, but still weighs something like 1.5 times the mass of our sun. So the density is incredibly high in these objects. They rotate with periods somewhere between 1.3 milliseconds, and actually it's higher than 8.5 seconds now. We now know that they can rotate as slow as 76 seconds. And they have a magnetic field strength of somewhere between 10 to the 8 to 10 to the 14 Gauss. They mainly emit at radio wavelengths, but they are detected across the entire electromagnetic spectrum. So they are detected as optical sources, radio sources, gamma rays, X-rays, and even all the way up into tera-electron volts. So they are very energetic sources. And here on the right-hand side is a schematic of what we think a neutron star might contain. It has on the outside a very, very thin atmosphere. Just below that is its envelope. Then it has a crust, which is like a crystal, You can see that in part B here down in the bottom left-hand side, sorry, where you have a lattice of these neutrons, and they're supported inside a so-called superfluid. Then below that, we have the so-called outer core, and below that, the inner core. And it's the physics of these inner regions which we don't understand. So the densities are so high in here that the molecules and atoms are all stretched and distorted in shapes. Sometimes this is called the pasta phase, because you get these long things a bit like spaghetti or penne or some sort of pasta. And it's in here where there's all sorts of interesting physics going on, and certainly physics that cannot be probed using telescopes. Using physical laboratories. You can't recreate these densities, and so you can't study this sort of physics in the laboratory. As I mentioned, they rotate, these objects, these neutron stars, they're rotating, and because they're so massive and so dense, it's very hard. They have a high moment of inertia, and that makes it very hard to change the rate at which they rotate. And that means that they make excellent clocks. So every time that the pulsar sweeps across your telescope, it's just like the tick of a clock. On the right-hand side, again, we're showing a schematic of what we think the magnetic field structure is around these neutron stars. So these neutron stars are highly magnetized. They have magnetic field strengths of something like 10 to the 8 to 10 to the 14 Gauss. You can see here that they have a this region here is called, where the field lines, these green lines are the magnetic field lines. These field lines close back onto the neutron star. You can see this is bounded by a region. This is the so-called velocity of light cylinder, or light cylinder. And this is where the field lines, if they were to still be attached to the neutron star, would have to rotate at the speed of light. And because they can't rotate faster than the speed of light, you see that some of these field lines, these ones here, don't close, okay, back to the neutron star. And it's along those field lines that we believe that the particles that generate the radio emission are accelerated. So you have radio emission is generated when these particles move along the magnetic field lines. And so you can see here what's shown as a radio beam. So that's the way the radio emission comes from. We think that mostly comes from quite close down to the surface of the neutron star. But the other emission that I talked about, like gamma rays or optical, is thought to come from this outer region of the magnetosphere, right near the edge of the light cylinder. So for purposes of most of what we're going to talk about today, what we're interested in is the narrow radio beam. So as the radio telescope sweeps by, you get a short pulse of radio emission, and then for the rest of the rotation, you detect almost nothing, or you detect nothing at all. And the other thing is the regular nature of the pulses that arrive at the telescope. So this rapid spin, where does that come from? Why do these objects rotate? So the neutron stars, when they're born, can spin, up to actually once every 5 milliseconds or so. And then but the vast majority of pulsars we know about spin around about once per second. This rotation comes from conservation of angular momentum. So the very massive star is also rotating, but it's rotating quite slowly. And what happens is when it collapses, the rotation is, the angular momentum is preserved. And that means that because the radius is decreased, the rate of spin must increase. And you can see that demonstrated here by this dancing ballet dancer, where they are showing that when they pull their arms in, their rate of rotation speeds up. And it turns out we can make pulsars that spin even faster than that. So the ones that spin at around a millisecond or so, we believe what happens there is that they are pulsars in a binary system, and the pulsar eventually slows down. It might turn off as a radio pulsar, but its companion star continues to evolve. And eventually what happens is that material from the companion star falls onto the pulsar and will spin it up to very high rotation rates. And again, this is angular momentum. So the material comes from the orbit, from the binary orbit, and the angular momentum from the motion of that is transferred onto the neutron star and spins it up. And these millisecond pulsars are said to be either recycled or reborn sometimes. And these pulsars are the ones that are used for things like gravity tests. And we'll get back to these a little bit later on. Okay, so that was the short introduction or reminder of what pulsars are. Now the question is, how do we go about finding them? Well, it turns out that radio pulsars are generally very weak objects. Okay, so their radio emission is very weak. They're not very strong. Excuse me, sorry about that. And so what we, the original discovery used so-called single pulses. So what does that mean? That means that you observe the sky and you see with your radio telescope at some moment in time an increase in the amount of radio emission that you detect, and then it drops dramatically so that the duration of this pulse will be a few milliseconds or so, and then you see nothing, and then the next pulse you see again maybe 1 second later, and then the next second, and then the next second. What this relies on is the instantaneous sensitivity of your telescope. You have to have a very sensitive telescope to detect these single pulses. Now, the brightest pulsars that we know about, the ones that were discovered very early on, of course, with modern telescopes, we can see these quite easily. But of course, they were difficult to see with the less sensitive telescopes from earlier decades. On the right-hand side, you can see an example of the discovery or the plots from the original discovery of the first radio pulsar by Dame Jocelyn Bell Burnell. And you can see how she detected this so-called piece of scruff, as she called it, where you can see the red here is the fluctuations of the radio emission detected by the telescope. And then at this moment, you can see an increase in the amount of radio emission that's detected, and then it goes back down again. And you can see that even way back when they first discovered radio pulsars, there was a problem with interference from other sources of radio emission, such as nearby tractors and things like that. Now, what makes this, excuse me, sorry, did that again. What makes this distinct is if you zoom in on this little section here, and so record the data with a higher time resolution, what you can see here are these dips. And these dips are occurring every 1.3 seconds. And this corresponds to the rotation period of the pulsar. And so this was how the first pulsar was discovered, using exactly this method of single pulses. It relies on the, as I said, on the instantaneous sensitivity of your telescope. You need to have a very sensitive telescope, but it also depends on, you know, how the pulse intensity of each individual pulse varies, right? Because sometimes it might give off the occasional very bright pulse, and that might make it easier to detect. This method of finding pulsars was used for quite a few years after the initial discovery, but then they realized that to find fainter and fainter pulsars, they'd have to go to other methods. But interestingly, a study done nearly 2 decades ago now by McLaughlin and Cordes showed that around about 1/3 of the pulsars show bright enough once in a while will show a bright enough single pulse that you should be able to detect about a third of the known pulsars via their single pulses. And just to remind you finally that this is a picture of, down here in the bottom right-hand corner is Dame Jocelyn Bell Burnell actually working on building the telescope. So not only did she find pulsars and had the wherewithal to recognize that they were something interesting and something astrophysical, she actually helped build the telescope that made the discoveries. So she, was a multi-talented person. This renewed interest in discovering or looking for pulsars via their single pulses, so these bright occasional pulses, meant that people went back and looked at old data that had been recorded and tried to search for new sources. And what they found was a population of neutron stars that emit radio pulses, but they do it irregularly. And so these are called the so-called RATs. The rotating radio astrophysical transients. And so they don't give off a pulse every rotation. And in fact, they don't even give off a pulse, in most rotations, which is what normal pulsars do. They give out pulses occasionally. And so these seem to be somehow, that we think they belong to the same population of pulsars, but for some reason their radio emission is more sporadic or sometimes called erratic. But these are interesting because it's important to understand the total population of radio emitting neutron stars in our galaxy. And this is where the single pulse search techniques can be very helpful. And even beyond that, it's how we've detected the fast radio bursts. So just to give you an idea of what I mean about the pulsars not always being equally bright, here is a pulsar called B2020+28. These are some observations with the Lovell telescope at Jodrell Bank. And the top plot shows you the average pulse profile from a few, something like 200 or 300 pulses. But what you can see here is in the bottom plot is a stack of all of the individual rotations of the pulsar. So what we do is we take the full rotation of the pulsar, we zoom in on when the pulse occurred, and then we plot above each new pulse, we plot one above the other, and we call this a pulse stack. So in this case, time is going upwards on the y-axis, and so each one of these is a new pulse, and the color corresponds to the brightness of the pulse. So you can see that these bright yellow pieces here are much brighter pulses than, say, in here, okay? And so some of these may be bright enough for us to be able to detect them. This next plot shows you the examples of the things that I mentioned called RATs. So here what we plot is the dispersion measure. So, oops, pardon. What you may remember, we discussed dispersion measure previously. That's the influence of the interstellar medium on the traveling of the radio waves through the interstellar medium. They are delayed so that the lower frequency radio emission arrives later than the high frequency radio emission. So we need to correct for that dispersion in order to be able to find these pulses. And so we plot this correction called the dispersion measure on this axis, and on this axis we plot time, and this is showing intensity. So here we can see a bright pulse here and a bright pulse here. So this object, which is an RAT, is only given off a pulse once every 800 seconds or so. However, by taking the difference in times between the pulses that we've detected, we know that it actually rotates with a period of just a second or two, but it's only giving off a pulse once every 300 or 400 rotations. And you can see other examples here. So this one at the top, for example, is given off 3 pulses over these, well, actually 4 pulses, if you see a very weak one here, over 2000 seconds. So these are the so-called RRATs. So how do we actually search for the single pulses? Well, so what we've got to start with is the, on the left-hand side, we can see we get the raw data from our telescope, a bit like the telescope there in Ghana. We take the data from that, and it looks something like this. Okay, so this plot here is what the raw data would look like if we looked at it, if there was a very bright pulsar in here. Okay, and so you can see, you maybe just can see, but I'll explain to you here that this is time on the x-axis here, and this is frequency on the y-axis. And what you're seeing is these lines that are sweeping through the data like this. This is the dispersed pulse. Okay, this is before you've corrected for the dispersion measure. And so this shows how the pulse is delayed as a function of time. And so what we need to do next is that you can see there's some spikes in the data just here. Okay, so these spiky data here, this corresponds to interference. And so we need to remove that interference from the data. And we call that radio frequency interference, or RFI. And so when we remove that, we see the data looks a lot cleaner, as we see below here. And you can still see those nice sweeping pulses as they sweep through as the bright lines. Now, when we're looking for new pulsars, we don't know initially what the dispersion measure of the pulse is. So what is that delay as a function of time? We don't have any information about that. And so we need to try different dispersion measures for each of the different epochs. Okay, sorry, we need to try different dispersion measures to try and detect the pulse. Okay, and here we can see we try all these different dispersion measures. Often we have to try many thousands of different values for the dispersion measure to try and get the correct one to optimize the detection of the pulse. So what about this radio frequency interference? So where does that come from? Well, interference can come from terrestrial communication devices. They emit in narrow frequency bands, like what you can see here is some examples from the Meerkat telescope, for example. You can see a plot here. This is showing a pulse. So this is the pulse here. But you can see there's this noisy bit of data here. You can actually see some lines here and here, and also probably just faintly here. Now, if I collapse this data in this direction, then I get something called a band pass. And if we look at that band pass, you can see that there's interference located here, here, and here. And often we know where this interference comes from. So these two, so some of this data is, these two regions are from global positioning satellites. So it might be GPS, it might be, what are the other ones called now again? I always forget. There are other, Galileo is one from the Europeans. There's also a Chinese one, and also a Russian one. So they emit in these ranges. And so these are satellites, of course, so they're very hard to escape. They're removed from your data. And down here is the contribution from the mobile phone. But if we remove all of these radio frequencies, then you can see that we get a much improved data. So radio frequency removal is very, very important. And it's an important area of development to improve the methods by which we can remove this interference automatically from our data. So here's the de-dispersion that I was talking about. I won't go back over that again. Here is a map. So this dispersion is due to the electrons in the interstellar medium. So the free electrons that's been ionized, the radio waves interact with those electrons, and this causes the dispersion. And what we show here is an example of where those electrons are located in our own galaxy. And this is mainly worked out from studying all sorts of things like pulsars themselves, but also looking at gas clouds, H1, and all that sort of thing to locate where these electrons are. So this is a so-called ATOF projection showing the galactic, the galaxy. So here along this axis is the galactic plane. This region in here is the galactic center. And you can see the variation in the dispersion measure here. And you can see that it varies. This is a logarithmic scale, so it varies all the way up to a few thousand right in the galactic center here. So depending on where you're looking, the dispersion measure can be very different. And this is what we're plotting here is the maximum dispersion measure. So if you integrate it all the way along the line of sight in that direction, but we don't know where the pulsar is along that line of sight. Okay, and so it may lie anywhere along that line of sight. So we don't know beforehand what the dispersion measure will be, and it can vary dramatically wherever you are in the sky. So that's why we have to search in dispersion measure. So here's just showing you what happens when you try different values for dispersion measure. So this is some data which has a pulsar in it. It has very bright pulsar, and we should be detecting a single pulse from it. And on the left-hand side, I'm showing that same piece of a piece of frequency on this axis against time on this axis. And I've dispersed the data, but with a dispersion measure of 0. So all I've done is added all the frequency channels together. And then on the right-hand side, you can see the result of that. And you can see that there's no evidence for any pulse at all. Now let's try a value for a dispersion measure of 100. Again, you don't see any evidence for any pulse. And it still basically looks like just noise on the left-hand side here. Okay, so if we try a dispersion measure of 190, we're starting to see something interesting in the towards the center of the data, right? We're starting to see a hint of gray down here, darker gray down here, but there's still a bit of a slope to it. So it's still got a bit of a curvature to it. And you can start to see that there's a bit of a rise in the intensity in this location as well. So we're probably getting close to getting the correct dispersion measure for this source. And then ultimately, if we get to the correct dispersion measure, so remember, this is all exactly the same data that I'm showing you here, just de-dispersed. So all the frequency channels are shifted to the right value, so they're aligned in the right way, and you get the pulse detected at the correct dispersion measure of 206.6. Okay, so just to clarify, and just to remind you that to correct for dispersion, what we do is we have to shift all of the frequency channels by a certain amount of time. And that time that we have to shift the frequency channels is proportional to this value of the dispersion measure. So in this left-hand corner, I didn't have to move the frequency channels at all. This one here, I've moved the frequency channels corresponding to a time which is proportional to this dispersion measure, and you still see nothing. But when we get the right dispersion measure, all the pulses at the different frequencies all line up, and we get a detection of the pulse. Okay, so dispersion measure is really, really important here. And so how do we actually make a detection? How do we decide? Remember, we can't look at all of this data by eye. It's not possible. So what do we do within our computer? Well, we try all of these different dispersion measures. And for each of the different dispersion measures, we try and detect the pulse automatically. So what we do is we find a piece of the data, or we take the data and we measure the statistics of the noise. So we calculate the statistics like the mean and the RMS. So the standard deviation, sorry, sometimes I'll use RMS, which means standard deviation. And so here what we do is we'll work out the standard deviation of the data here, and then we'll compare the total intensity in this region, so in the pulsed region, and we'll set a threshold, and the threshold is shown by this red line here. Okay, so the red line is the threshold, and that threshold, anything that's above that threshold, we will call a real detection. And we want to set that threshold at an appropriate level, given the number of dispersion measures we try and the number of data samples that we have in our data set. Okay, so we can make a reasonable assumption that these data are distributed in a Gaussian way, but we need to consider how many trials we're doing. And so sometimes, for example, in the searches that we do with Meerkat, we set this threshold at 8 sigma, so 8 times the standard deviation of the noise is our limiting threshold. So in the computer, we take our entire de-dispersed time series that we generated based on for each of the dispersion measures. So remember, we need to do this for many thousand dispersion or many hundreds to thousands of dispersion measure. And each one of those, we have a long series of time corresponding to our observation duration. And then we take that data, we calculate the statistics, and then we look for peaks above 8 sigma. And if we see anything above 8 sigma, then we store it for a human to look at. So here is what one of our candidate plots looks like when we're looking for one of these new sources. So in the top, you can see the usual time on the x-axis, frequency on the y-axis, and the software detected a pulse with a dispersion measure of 63. Okay, the white line here shows us the delay that we expect this pulse to have as a function of time, if it has this dispersion measure. Okay, so for each of these frequencies is delayed. And you can actually hopefully just see some black dots just to the right of this. And that corresponds to the sweep of the pulse in the data. In the bottom left-hand plot, what we show is the data after we have corrected for the dispersion delay. Okay, so we can see there's a pulse here. So we've corrected. So we've shifted each of these frequency channels to the left like this. And now we've plotted them and we've zoomed in on the pulse. Okay, so now you can see it's a nice straight line showing us that this dispersion measure is the correct value. And then if you add all of these frequencies channels together, you get this detection here. And up here on the left hand, in the text here, you can see it says signal to noise ratio 14.61. And this signal to noise ratio 14.61 means that the signal was 14 times the noise. Okay, so the signal is 14 times the RMS of the noise, or the standard deviation of the noise down here. And so this is the sort of plot that we would look at for determining whether we think the signal is real. So this is the end of the section on introduction to pulsars and also how we search for pulsars using single pulse search techniques. We'll take a break here and I will start the next video where we'll talk about using the Fourier transform techniques. Thank you.